Hello everyone, I'm Long Mai. Today we'll present a joint work with Professor Feng Liu at Portland State University. In this paper, we introduce a neuro-implicit representation for video. Neuro-implicit representation has been successful in representing 2D images. In image-based implicit representation, a coordinate MLP is used to map the 2D pixel coordinates into the corresponding color values. So, a standard extension of this representation to video data would be to add an additional input coordinate indexing the time t. However, this representation will treat video's data as 3D data. It does not reflect the nature of video as a collection of interrelated images relating to each other over time through motion. In other words, it's not clear how the motion information is encoded, and there's no tangible representation of motion to manipulate. So we decided to look at the problem from a slightly different perspective. We know that in practice, positional encoding is used to first map the input coordinates into the higher dimensional vectors using a collection of sine and cosine functions before passing it through the MLP. Viewing it this way, the model can be viewed as a mapping from a set of sinusoidal patterns to the output image content. Therefore, we hypothesize that by displacing the sinusoidal functions over time, it should be possible to let a single 2D image-based model to generate temporally varying content. Based on that observation, we introduce our neuro-implicit video representation. Our method uses a 2D image-based model MF as a frame generator, and we couple it with a phase shift generation model MP to generate a time-varying phase shift vector phi t. We then use phi t to shift the phase information in the positional encoding at each time t. This induces the positional encoding into MF to vary over time. For that reason, we call this phase-varying positional encoding. In this way, we can enable a regular 2D image-based model to generate video frames. Another advantage of this representation is that phi t, after training, can be manipulated at inference time. That can be used to modify certain temporal dynamics information in the video. For example, in this case, there's a strong vibration of the fork in the original video. Such vibration can be much reduced in the resynthesized version. This property makes our representation motion adjustable. Experiments on different video content suggest that our model with the incorporation of phase-varying positional encoding can still retain the ability to fit the video data well. Compared to the direct extension method, the learning problem faced by the proposed model is more challenging. That is because the phase information is constantly shifted over time in a way unknown to the frame generator. Despite that challenge, our experiments show that the model can still learn to fit the video data well and achieves comparable quality as the direct extension method. In addition to learning to fit video data, by manipulating the learned phase shift vectors at inference time, our model can also enable creating different temporal dynamics effects, such as motion filtering, motion intensity adjustment, and also video loop detection. Thank you very much for your attention. If you are interested in our research, please visit our poster for more details.